2. Okay, so in terms of cumulative, you've done cumulative frequencies where we were talking about a frequency distribute. I mean the frequencies of items or individuals, and the cumulative. We were saying you start with, say, if you had 2, 3, 5, you start with the 2, then you add 3, then you add 5, and you get 10. So we are adding them as we go along. That is what this means. This therefore tells you that if you want to get the CDF of a particular discrete distribution, you ask yourself, what are the values taken by the random variable? And if I'm looking for the cumulative, I'm starting at the beginning. I get the distribution for F. But now when I come here, I don't just get for 1, I also add it to the one I got for 0. When I come here, I don't just get the distribution for 2 alone, I also add it to the one for 1, which I had already, the one before that I had added 0. So I started with f of 0, that is the first one, small f, because I am starting with that, and that is now the same as my capital F. We use capital for cumulative. So if you have been using these notations interchangeably, please note that when we say PDF, it is conventional that you use the small f, so that the capital F represents the cumulative distribution. So if my x is equal to 0, it's PDF, meaning that I can substitute it in that distribution and I get the value. That value is the same as the cumulative value. Now, when I come here, I want to look for the capital F of 1. This will now be the one I got for 0, that is F of 0, plus now the PDF at 1, that is F of 1. Meaning I can substitute my 1. If, say, for example, I had a f of x, the small f of x equal to, say, 2x. So I am saying I'll get 2 times 1, that is my small f of x, and I'll add it to what I got for 0, cumulatively. So that if I want for 2, capital F for 2, I'll say I'll have what I've got here, which is now capital F of 1 plus the small f at 2. That is how you are working cumulative distributions for. It is a step function. When you plot it, you find you are moving in steps. This way, you are moving from one step to the other. So it's a step function. A continuous one would just be a curve, the way we know it. Okay, but this one cannot be a curve because of the fact that you are stepping from one value to the next. So if you plot it, even in your reference, you will see it is a step function, meaning that you are jumping from one to the next. So this is how you determine cumulative distributions for discrete cases. But now when it comes to continuous, you would look at the interval you are given. The interval you are given, say, for example, somebody says x, your small x is greater than 0. And then he's asking you for probability of x less or equal to 2. Then that means you are going to integrate from, you are looking at a situation of the lowest is 0 and the highest 2. If you are looking for the probability. But now when you are looking for a general expression for cumulative distribution, then I would say probability of the x less or equal to x. That is the general definition of cumulative frequency distribution. So you say the lowest was supposed to be 0, and I'm being told up to x. So the highest value should be x. And because this function, this expression is supposed to be in terms of x, we introduce, like, for example, if I had, say, 2x as my PDF and it's continuous, I would now use a different variable just to facilitate the distribution. So I'll integrate that in what I had as my PDF as 2x. Now I'll call it like 2t dt. So that when now I integrate this, now I will substitute from 0 to x. even though this expression now will be, like say this one will be 2t squared over 2. So I'll put my 0 here, and I will also put my x here. So I'll get my 2x squared over 2. Okay, so I'll still come back to the function. So I'm just introducing a new variable because my upper limit is in terms of x, and therefore that is the expression we cannot still differentiate with respect to x when our upper limit is x. So we just use a different variable to facilitate integration, so that when we come here, now we substitute, and therefore now you can see I will substitute x here, and I'll have 2x squared over 2, which is a function. So this is now called the cumulative distribution function. Okay, so I hope that is clear. You had already looked at that, but I wanted just to clarify so that you can be able to distinguish between PDF and CDF. If somebody has a question or has done something, some example, or there was a question you are given and you did it and you are not clear, please let me know so that I can allow her to continue. Anybody who...
Yeah, yes? Excuse me, sir.
Yes,
I just wish to confirm that when you're given the range, the first maybe step you can take is to integrate over that range, and you'll always get a 1.
Yes, that is to show that it is a PDF. If you don't get 1, then it's not a PDF.
Thanks.
Yeah. So when you now want the CDF, then you now, if the range is from 0 to infinity, of course, if it was from 0 to infinity, I will integrate and get 1 just to show it's the PDF. But now if I want a CDF, then I'll use this expression: probability of x less or equal to x. Now we'll integrate from the lower value. In our case, the lower value is x. It doesn't have to be 0. It depends on if it was -1, 2, 3, the lower value will be -1. But now I'll go to x. I'll change the variable of integration for facilitative purposes. I will integrate it with respect to that variable, and when I come here now, I substitute my x, and I will be able to get an expression in terms of x, and that will be my CDF if it is continuous. Anybody else? Iko sawa? If we are fine, please. That is what I wanted to illustrate at this particular point. How about, okay, which other, before I ask her to continue, which other area is, you may have a challenge, something that you didn't get? You know, he said this thing is participatory, so that we don't just come talk and you start quarreling the way Peter is quarreling. I want us to let us get it. If something is not clear, you stop us in the middle, and then we clarify it so that it is clear to you.
Yeah, excuse me, sir.
Yes, yes.
Yeah, there was the bias rule. She explained very well, but
Yes.
maybe you could give us your point of view so that we can have a
the bias rule.
Yeah.
Now, you have the what you can if you remember Venn diagram in set theory, you have this set, the overall set, and now in probability theory we are calling it sample space, the whole of the outcomes. This is the one we are calling the sample space. Okay, now I could have 2 events. Okay, and I could have another event that cuts across them. Okay, so I may want to find if I have these 2 events A and B, and then I have, say, this as C. This C cuts across these guys. Now, what bias is saying is that is there a possibility, or is there a relationship between these 2 guys and the guy that cuts across them? I'll give you an example. you want to be a student leader, or maybe let's say some club, let's say this thing we hear of members club, for example. You want to be a leader. So you have maybe 3 individuals who want to be maybe chairman. So there's the probability that this guy will be chairman, probability that this guy will be chairman, and the probability that this person will also be chairman. Those are chances. But there is something common to them, which has been passed maybe by the board, that there will be increase in membership. So this one now, somebody cannot campaign and say, me, I'm not going to increase the member. It is already agreed that when each one of them, whoever is elected, there's going to be an increase in membership. So this increase in membership cuts across all these guys. And that's what I'm trying to say. This is like this event here, cutting across. So somebody then will ask, there's a chance that this guy will be elected, maybe 0.3. This guy will be elected, say, be 0.4. This guy elected 0. Something. Now, once we have those chances, we have this particular characteristic, do I call it property that must be, or a resolution that must be implemented. So this resolution is cutting across. So I cannot say, me, when I am elected, I will not increase membership fee. No, that's already agreed that we are going to elect, to do elections, but there is going to be an increase in membership after that. So this is agreed. So this is like the common event. So somebody may want, what is the chance that there will be increase in membership if so and so is elected? Or what is the chance that so and so will be elected given that there is membership? So it is conditional. So what this guy is saying, can we just determine based on the chance that these guys will be elected to get the probability of the increase in membership? One thing we are saying, what is the probability of this event that cuts across? What is the chance it's going to happen when we are given these chances? Okay, so with that, then we are asking ourselves, what is the chance that so and so will be elected if there is an increase in membership? So that is what Bias is trying to do. It's telling us that if we have 2 events, A and B, and we have another event that cuts across them, can we express this particular event in terms of this? Okay, so we are looking at a situation where we are saying probability. We know from conditional probability that probability of A given B is probability of both A and B occurring divided by the probability that B will occur. We want to use that concept. We want to use that concept of conditional probability to be able to determine the probability that what is common for all the events will occur. That's one. 2, what is the probability that this is going to occur given that this has occurred? Or what is the probability that this occurs given that this has so and so has been elected? So that is what that formula was telling you, that you can be able to determine the probability of A. For example, if this event here we call it, say, membership M. Okay. So the question would be, what is the probability that there will be an increase in membership? But you're given information about the probability of these guys occurring, okay? The probability that maybe increase in membership given that this person has been elected, increase in membership given that this person has been elected. So you're given additional information. So what do you want to do? You want to find a way you can be able to determine the probability of this the probability of this common event, and you have these individual events. That is what we were discussing first. Then you can also now say, what's the chance that A will be elected given this an increase in membership? And that is where they were saying you can now say probability of M given A times the probability of A over the sum, because now you have many of them, because it's supposed to be probability of M down here, but the probability of M you write in terms of the sum of the probability of M. Suppose they were just, if I was using A1, A2, A3, then I can say AI's probability of AI times probability of AI. But if it is AB, I can B and C, I can just say probability of M given A plus times probability of A plus probability of M given B times probability of B, and so on. So in essence, this denominator basically is this probability, the probability of M, the probability of that particular event occurring. So that formula was just trying to tell you there's a relationship between the known events and the one that cuts across them, so that we can be able to determine the chance that this is going to happen given that this has happened, and therefore we would then condense them into what we are calling the Bayes rule. So understand the Bayes rule in this context, that you have various events, identify the common event for those various events. Now give the expression for the common event, this one, which is usually this denominator, and then once you know it, then you can now be able to determine, so long as the information is given for the individual probabilities, the information is given for the occurrence of the common event given these individuals, and then from there now you can ask yourself, what is the chance that Ochor will be elected given that there's an increase in membership fee? So we are now getting your chance of getting this. These probabilities are based on prior information or what is known about you relating to the members. But now we are determining it scientifically or statistically to tell you that yes, with this membership increment that has been agreed, you have a high chance of getting it based on your past or what is known about you. I don't know whether, Char, that gives you a clear understanding of Bayes rule. Just in
Yes, it does.
Summary. So from
we
here you can be able to determine the various probabilities, but you must be given the individual probabilities and then the probability of this common event given these guys, and then with that, then you can now change it, because conditional, we can get probability of A given B, and we can also get the probability of B given A at the same time. It's possible, so long as I know these guys, I can be able to get this. So in this case, one of these is given. You see, like I'm now looking for A given the membership, so it means that the membership given A were given to me, and therefore I can now apply them in this formula and determine probability that these guys will occur given these other guys, this common event occurring. I think I don't know whether Malim is here. She can then continue.
Okay.
Now, did you mention the gamma distribution?
No.
The gamma distribution?
Yeah.
Samuel, do you have the reference with you there?
No, I just have my notes, my class notes.
Oh, okay. Who has the reference? Okay, Angela, take me to that point. That just share that part of gamma distribution. I just want to. Those are distributions that are very important in. We are not going to into the details, but I just wanted to mention that as one of the distributions that would be very useful in engineering. We define what we call gamma of gamma. The gamma notation is this one. Gamma of alpha is the same as alpha minus 1 factorial. Okay. This, we are not mathematicians per se, we are just using, but these ones we can play around with in Jerome, not here. But here, by definition, gamma of alpha is equal to alpha minus 1 factorial. So that if you wanted gamma of 3, then this is equal to 2 factorial, which is 2 times 1. And the gamma of 1 is 0. You have a lot of material there and a lot of questions to try and play with. When you say you are busy, then it means you have no time for this unit. So it becomes a bit strange because it's supposed to be part of your what you call busy. So yes, so the gamma distribution, you can read all those stories. I just want the expression. Let's go down. Now, exponential is a special case of gamma, by the way, and exponential is useful also in modeling queuing theory. You see queues in banks, queues elsewhere. We can be able to model them using exponential distributions. They are basically exponential is a continuous distribution, and they are also related to Poisson. When I am studying the arrivals, the way the customers are coming into the bank, you know, customers are discrete. We count them. So these customers, they are coming into the bank and they are queuing. Okay, that aspect is discrete. And as you were told, Poisson distribution is a discrete distribution. What has happened? Poisson distribution is a discrete distribution within a continuous interval. In other words, you are saying these customers are coming into the queue, and these customers are countable. But then when it comes to the queue, we are looking at the interval time between this time and this time. You know, time is continuous. So you're looking at discrete arrivals in a continuous space or time. So you are saying within the limit of 2 hours, 10 to 12, how many customers arrive? You know, you are looking at between 10 and 12, and you're talking about continuous. So, but you are now talking about who arrived or how many arrived, meaning you can be able to count them. So Poisson process is used at that particular level. Now, when it comes to a service at the counter, you are asking yourself the average number of customers per unit of time, or in most cases, how much time per customer? How much time did you take serving a customer? You know, the question you're asking is continuous. And therefore, now you would use the exponential distribution. So we can use two distributions in the same process, the queuing process. Those arriving, we use Poisson because they are discrete within time interval, which is continuous. But then at the counter, now we are using exponential because we are talking about time per customer. And therefore, time being continuous, we use exponential distribution. But what I wanted to emphasize here, by definition, a gamma of anything is equal to that minus 1 factorial. And therefore, just using that, we can then put this in equation form, and as you can see there, it is e power negative x, x power alpha minus 1. So by definition, we can say gamma of alpha is the integral from 0 to infinity x power alpha minus 1 e power negative x dx. So in essence, if you want to get gamma of alpha, you integrate this by parts. The integration by parts should be able to lead you to alpha minus 1 factorial. That's what we were saying, that it will lead us to alpha minus 1 factorial. So just go down to the gamma is the function. No, the gamma function. This is being done by integration by parts. You have learned that, so we don't need to belabor that. What we are saying is we can be able to determine this. So now the gamma distribution has two parameters or two unknowns, alpha and beta. So we once you have the gamma distribution given in terms of the gamma function, this is the gamma function, then you can be able to determine its mean and so on. So the mean of the gamma function or the gamma distribution the mean is alpha times beta. That is the product of the two parameters it has. The variance is alpha beta squared. So these distributions are important. You should have an idea how they look like and their uses. They are being explained there. So later on, or at a higher level, you may be able to apply them in now undertaking your projects, especially either the final year or at master's level. But it's important that we know what distributions they are. Now with this gamma, you can then generate many distributions. For example, if alpha, because gamma has alpha and beta, if alpha is equal to 1, then you have what is called the exponential distribution. In other words, you can generate distributions, other distributions from the gamma distribution. So I wanted you to get that. I think when it is equal to 2 and beta is equal to n over 2, it will go down. Beta is equal to n over 2 or something. We have what is called the chi-square distribution. Now, those graphs are just indicating if we vary the alphas and the gammas, then how fast do we get to the normal distribution? As you can see here, when alpha is 4 and beta is 1, we see we are saying let us have a beta constant, and then we vary alpha. Then you can see we are tending to the normal curve. Okay. In other words, as the gamma becomes larger, you tend to the normal curve. Those details of the distribution, the parameters of the distribution behaving as the sample size goes up and so on. Those ones we can do under sampling distribution. But what he is trying to illustrate to us is when alpha and beta are the same, how does the distribution look like? And when we now vary alpha and beta is constant, how does it behave? So that is how that particular diagram is illustrating to us the behavior. There's something called central limit theorem. I don't know whether you came across it. It is the one that tells us what happens as certain values become higher. In terms of sampling, we would talk about that later. When you pick many values, most of the distributions tend to normal. So all these distributions you have come across, with them, there are certain situations that they tend to the normal. You see, binomial tending to the normal, Poisson tending to normal. All these, even continuous distributions, would tend to the normal. The normal distribution is the most important distribution in statistics because most real-life situations follow a normal distribution. So we tend to look at, if I have this distribution, under what circumstance would it be related to the normal, or would it be said to be associated with the normal distribution? And then we can now use the Z tables that we are going to look at. Just go down, we see the chi-square, how it looks like. Yes, so that chi-square, you will find it when alpha is equal, I think I've done it the other way around. Alpha is equal to n over 2, and beta is equal to 2. Okay, so these are now special cases of the gamma distribution. And if these guys have what we will now call later on degrees of freedom. Now, especially the chi-square, we will now use the what is called degrees of freedom. I'll explain that later. But now, I just wanted to you to appreciate the gamma distribution. Okay, it is, I think, related to some aspect in engineering where they apply it, and then it's mean variance, and it's special cases when it is alpha is equal to 1, we have an exponential distribution. When alpha is equal to n over 2, beta is equal to 2, we have what we call chi-square. This one is now called chi-square distribution. I'll mention that later when we are looking at sampling distribution. And this chi-square has what is called degrees of freedom. We will mention again that. So, but you must, when you are going through that area, just appreciate that these are special cases of the gamma distribution. Okay, and they can help us to be able to solve various problems. Now we will come to that when we are now determining the probability that maybe an item is likely to, the lifespan of, you see, like your engineering products have lifespans. So is it possible to predict the lifespan of a particular outcome from a production line? That would be very important for us, because you would want to use some certain materials after a certain period, and it would be important to know how long they would last. So we will be able to apply those concepts later. But I just wanted to illustrate that when you are looking at distributions, there are so many, but now we will be interested in which ones are very important. Like with the discrete distributions, binomial is very important, especially those who are in production, where you would want to check whether you have defective or non-defective items. Its beauty is that it deals mainly with two possible outcomes, either success or failure. And therefore, from there, you can be able to determine what is the chance that these items are producing will be defective and so on. So that is important at this point. So sorry, Angela, you can now.
Excuse me, sir, just something quick.
Yes.
Yeah, I know you had said earlier that machine learning is a bit too far from us right now. Yeah, but I was requesting if maybe you have some undergraduate students in computer science or data science or statistics who will maybe be have an understanding at our level, so that we can just interact with them peer to peer. Because I don't understand why, as engineers, you are in the other side of town, and you guys are there at Chirom, where real mathematics and those things happen. I believe
Yes.
our fields are interrelated, and we are usually isolated there, and
Sorry.
we
Yeah.
don't have an important
Yeah. That
grasp of this
interaction is
concept.
important. I agree with you. We will see if we can be able to have some interactive sessions, maybe face to face, if time allows. Maybe because the semester is almost. You are breaking around 15th. Yeah. Is it?
Yes.
Yes. So we may, but let me discuss that with my students and see if we can have some interactive sessions.
Yes, that would be very nice.
Yeah. Okay. So. Let's allow Angela to continue with what she was doing.
So confirm if you are able to see my screen.
Yeah, it's okay.
Okay, so I was saying, as we have been told by Prof that this is the normal curve. We have seen the normal curve. It looks like this, and this is it is called the standard normal curve. This one, it is symmetrical with the zero in between. So when we say phi of z, that z is taking values from negative infinity to the highest value of z. This z here on this curve is here. So z is ranging from this other side up to the z. So the shaded region here is the phi of z. It is the cumulative functions of the standard normal. So this is the shaded region that we are interested in, and this is the normal curve. So the values of z are tabulated in the table.
I think that was an error. It's supposed to be phi. It's phi of z, not x. Sorry, phi of z.
Yeah. So we are going to see how to find these from the statistical table. I had told the class rep that we will be going to use the tables on page 736. So for an example, how do you find the probability that z is less than or equal to 1.25? Now here, where there is z, it is 1.25. So how are we going to find the probability? We're going to use the Z tables. They will give us the probabilities. So let me just share the table. We read 1.25.
So when she says less or equal to 1.25, you are looking at values from 1.25 going back, because the curve is from negative infinity to positive infinity. Okay, and therefore the total area under the curve is 1. That because we are familiar with that the total area under the curve is 1, because that integral from negative infinity to infinity is supposed to be 1. It's a PDF, and that is why we are saying we are looking for that area from the to the left. Sometimes I just use the word to the left of 1.25. Just go up to the end. The tables are before the, just go, yes.
So there are so many tables, but we are looking specifically for the normal one. So I think this is the normal table that is giving us the values. We have been given the values of Z. So when you want to read the probability from this normal table, 1.25, you just look at Z where we have 1.2. It's here. Down here, there is 1.2. Then you go towards the right. You look at where there is 0.05. So we have this value 0.8944. That is the Z score from the table. So this is the probability. When you look at this normal table, it ranges, it goes up to the maximum value of, what is it?
0.999 something.
0.99, that is almost 1. That is the maximum value of the probability. So when you read the Z table and you have a value more than 1, you just know that you are wrong, or maybe you are using a wrong table.
Now that zero, the value we have read is covering One thing that I also, as she is looking for the table, when you have the Z table, when you have the Z curve, the Z curve is symmetrical. The mean is 0. That is why we have 0 in the middle. The area to the right is 0.5, and the area to the left is also 0.5. Now the values here are negative Z values. Why? This is a number line. When you have 0 to the left are negative, these are Z positive Z values. So when she's talking of 1.25, it is here. Okay, it is on the right. If it was negative, we would put it on the left. Okay, so the area, this is area. It has nothing to do with negative or positive. Area cannot be negative. So regardless of whether you're talking about the negative or the positive Z value, you will still have a positive area. And that area cannot be more than 1. So what the table has done is, it has, this is known. This is 0.5, it's known. So it has just added some value here. So if you are talking of 0.8 something, if you remove this part here, which is 0.5, then the area between 0 and the Z is the, some tables you will find are only giving you this. But if you are looking for less or equal to 1.25, please always add the 0.5. But these tables have already added the 0.5 plus this area here. So this area, sometimes the table only, you will find a table which is only, this part is the only shaded part. So if you find this as the only shaded part, you know that that table is only giving you this area. And that's not the area to the left of 1.25. The area to the left of 1.25 is that area plus 0.5, because those tables are assuming that you already know that this area is 0.5. But for this case, it has already been added. And that's why the shading includes even this area. So I was just trying to illustrate, to remind you that it is possible that you can only have tables where it's only this portion, 0 to Z, is shaded. Don't worry about that. Remember that to the left, there is 0.5, that is standard. Or if it is this other side, you'll find it's shaded only that small portion. It is assuming that you already know that this part is 0.5 because the total area is 0.1. No, sorry, the total area is 1. So therefore, that is why some tables only have this shaded, and that shaded is the one they are putting there, but that means you need to add 0.5 all the time. But if it is shaded up to the point, like in her illustration, then that area is covered 0.8 something. Okay, like if you are using this table and it is, this is 1.25 is positive. Now, if it is negative, the best way to be able to determine these probabilities is to shade, not to shade, to sketch. You sketch and identify where is this value. So if I gave you, say, negative 0.18, negative 0.18 would be here on the left of 0. So it will not be the entire shaded part that we were looking at. So in this case, if it is less, we are looking for the left of that. So the left of that now, we will say, because of symmetry, negative 0.18, the area between 0 and negative 0.18 is the same as the area between 0 and positive 0.18. Because of symmetry. You have to remember that for the normal curve, it is symmetric. So whatever value you are given, if it's negative, know that when I'm at 0, if it is negative, I go to the left. That area is the same as going a similar distance to the right. So don't worry about the negative value. You'll still get the area from that table. For example, here, Samuel, what is 0.18 from the table?
I'm sorry, but I didn't carry the table. I got the message
You
from
can't
the
see
class.
it. You can't see it from.
I'm using my phone. I'm using my phone, so I'm viewing your screen.
Oh,
I can't view the other one simultaneously.
oh, okay. Anybody who can view it? Or
It's 0.5714.
0.
0.5714.
5714. Okay, for 0.8. So what that is telling us is that this area, that's now positive, the area to the right of 0.18, because we are looking at a positive 0.18, 0.5714. Now, 0.5714 covers 0.18 on the right, but we want the left of negative 0.18. So what do? This area, this is the area we want. The left of negative 0.18, but we've already gotten 0.5714. I don't know whether I'm clear. If I'm not, let me repeat. Let me sketch. I have the center. I have negative 0.18. Okay, so I'm looking for this area, the left. But I have this 0.5714. This 0.5714 is this area from the positive one, 0.18 to the end. But I want this one. How do I get that area? Or would I take this? This one is more than 0.5, therefore I can't take it. In any case, I would only take it if it was going up to this side, because it's more than 0.5. Up to 0 is 0.5. So, but now I have 0.5714. So how do I get what? How do I get this?
I think
this, yes?
I think we'll subtract 0.5 from 0.571.
Yes, we subtract 0.5 from 0, because we just we want this area here. We want this area, up to here is 0.5. Now, what we have is this one. Let me illustrate. I have this up to the end. But I have up to 0. I have up to 0, I know it. It is 0.5. So, but now I'm going up to 5714, which takes me up to this, to the end. So this is the area, and I am looking for this part here, between 0 and 0.18. Obviously, I have to subtract 0.5 from here so that I get this small area. And this small area is the same as this small area, between 0 and negative 0.18. So if that is the case, therefore, I am saying that if this is the area up to the end, I'm looking for only this part here, then I have to know this area. So what is this area? I have to know it. So if I have 0.5714 and I remove 0.5, I'll get 0.0714. This is this area here. 0.0714 is now the area between 0 and negative 0.18. What is remaining for it to be 0.5? So I'll say 0.4268. I don't know whether that's true. 0.005. This area here is 0.4286. Because this area here is 0.0714. This small one, between 0 and negative 0.8, is 0.0714. And I want to the left of this. To the left of this is this one. Now, the other easier way is you've gotten this. If your table was giving you that 0.0714, it would have been very easy. This one would just be 0.0714 and then the remaining part, either left or right. The remaining part that I'm looking for to the left is the same as the remaining part to the right. So if I knew this, I would just still say it's the same area. Area is not negative, and therefore we are just talking about symmetric. So you have negative 0.18, you look for 0.18 from the table. Then you ask yourself, where is it? And that is why, let me put it as a must for you. Please sketch. Before you get those areas, just sketch a normal table, put 0 in the middle, and ask yourself, this value I'm talking about, is it to the right or is it to the left? Let me put there. So which region is being looked for? Greater. Greater means to the right. Less means to the left. And then now I'll go to my table and ask myself, what area is this table giving me? Okay, so you identify the area, and you had identified the region you want within that particular sketch, and therefore you will be able to subtract appropriately and get that area. Angela, now you can continue.
Okay, there is another case whereby we have a range of Z. Like for an example, if Z is ranging from A to B, for example, this one, if you have a range from X is ranging from A to B, then how do we find the Z score? First, we assume that it is in between these. If we have the mean, if we have the mean of the distribution, then we simply use the lower bound A minus the mean over standard deviation, and then the upper bound will be the B minus the mean over standard deviation. So if you have been given the mean, this is how we are going to find the range of Z. And then after we find the values of the range of Z, we simply subtract. We read from the table, we take the value for the upper bound minus that of the lower bound. So for an example, if we have a random variable with the mean of 50 and the standard deviation of 10. So we want to compute the probability that X is ranging between 45 and 62. So here we have been given the range of X. We have been given and the standard deviation. So how are we going to find the probability? We simply check the lower on the lower side, we take the value minus the mean over standard deviation, and then for the upper side we take the value minus the mean over standard deviation. So
yeah, so let me clarify something here. When we are learning how to use the normal curve, the first stage is to assume the Z values, and then we learn how to read them from the table. That's what we have done in the first part. We talked about Z less or equal to 1.25. I gave an example of Z less or equal to negative 0.18. The next one, before we go to standardization, is suppose I'm looking for the probability of, say, 1.21 less or equal to Z less or equal to 2.11. Let's illustrate this before we go to the standardized values. So here we are looking for area between 1.21 and 2.11. So we'll come here, because both of them are positive, we'll come here and look for we put 1.21 here and 2.11 here. Okay, so with that then, we will ask ourselves, how do we then determine this shaded area in between? So the area in between, we should be able to know how to get it. That means that from the table, I can get the area from 2.11 backwards up to the end. So that is the probability that Z is less or equal to 2.11. That is the area from 2.11 up to the end. Then I subtract, because there's also the area from 1.21 up to the end. 1.21 up to the end. So I'll subtract the area, Z less or equal to 1.21. That is just the difference between the two. So in other words, if these guys have similar signs, I'm talking about both are positive or both are negative, then just get the area for the larger value and subtract the area for the smaller value. That because you are looking for area between, you have to know the area from 2.11 up to the end. You also you have to know that you'll read from the table. Then you'll also read the area from 1.21 up to the end. So what is remaining is the difference between the two. That is very simple. Now the other possibility could be one is on the other side. I want so that you can understand what she's telling us now, that I have, say, negative 1.10 and positive 1.23. Now you can see this one, I'm also looking for the area between them. Okay, I'm looking for the area between them. But one is on the left, the other one is on the right. Okay. So obviously, I will get the area to the right of 1.23. That is easy. That one I'll read from the table. Okay. I need the area to the left of 1.1. But you see, it is not this one. It can't be this negative 1.10 to the left, because this one is just a portion. It is like you are here, positive. So you must know this area here for you to be able to say, I now know the area, because 1.1 is this side. The table gives me 1.1 on this side and so on. So I need to know this area to the left of negative 1.10. I need to know the bigger area, which is 1.23. Now, I don't know how you would want to do it, but one would then look at the table gives me this, and the table gives me for 1.10. So how do we then determine the area in between them? Okay, how do we determine the area in between them? Now here, I can get this area, 1.23 from the table. That is up to the end. Now, if I decide to subtract 0.5 from that area, then I'll get this part here. If I get for 1.1, because it will be on this side, assuming the negative, I'll get it to include 0.5. So one way is get for this guy and subtract 0.5. Get for 1.1, subtract 0.5. Add those two areas and you will have these two areas. I don't know whether I'm clear. Because 1.1, if it was negative, it will be here. So we will read to the right, to the left. 1.23 will read to the left. So once I get 1.23, it already includes 0.5, sorry. So from here to the end includes this 0.5. I remove it. So I remain with 0 to 1.23. That's one part of the area. 1.1, I remove. I read it, it includes 0.5. I remove 0.5. That gives me this area here. So for me to get the area, I would add this area to this area. But how do I get those two areas? I just need to get for each one of them, and for each case, I subtract 0.5. So I don't know how we can put it such that we get the probability of x, sorry, z, not x. Here we are not using x because we are assuming we've standardized. So z less or equal to 1.23. I want to subtract 0.5. Then I also get probability of Z less or equal to 1.1. Then I also want to subtract 0.5. So these two, when I add the result, then I'll get the area in between. It is a bit tricky when you have one value on the other side and the other and one value on this side. So the first thing we have done is we know a standard normal curve. We have the given specific, we already, sorry, we assume we have the values. So we are learning how to read the table using a particular value of Z in between, Z in between values of the same on the same side. And then we are also looking at values on different sides. Then now we go to what she's doing. We now have an example of a measurement in X, which will now be told what is the probability that this measurement will not exceed this, or will be less than this, or will be greater than this. Then now we standardize. When we are now given the X, we cannot check the values of X from the table. We have to do what? We have to standardize them, change them to, that is why she's talking about X minus mu over sigma. That is standardizing, changing that X to Z. And once you've changed it to Z, then is when you can go to the tables. Sorry for that. I just wanted to clarify that so that they understand what we are trying to do.
Okay, so if you have a range, you have been given a range of X. First of all, you standardize by taking the lower value minus the mean over the standard deviation. So here we have a Z. It has changed from X to Z because we are standardizing. So we will take, so here when you do this calculation, we will have the value for the upper bound. So we'll read with the tables, we read the upper bound minus the lower bound. But as you can see, for the lower bound, we have a negative 0.5. So first of all, for the negative, we say 1 minus the positive of that, because now we don't have negative 0.5 in the table. So we are going to say 1 minus the value of that. We will read 1.5 from the table, and then we subtract from 1. That will be for the lower bound. And the upper bound, 1.2, we read directly from the table. Then we find the difference, the area in between them, so that we have the probability that X is ranging from 45 to 62 is this one. So in the question you are given the X, it is upon you to standardize before you go to the tables. So anybody with the challenge reading the Z tables?
To some questions, I don't know whether you have them so that we can practice. They do them and we check.
So there are some questions here about finding the probabilities, the exercise.
Yeah, let's start with the first one.
Yeah.
Oh, you have done them.
No, this one, it's just the beginning. They are supposed to finish. Then for question 2, they do them on their own. So for the first one, you have been given the range of Z. Here, you have been given the range of Z. So we are going to read from the table 2.75 minus 1.25, because here this is Z. But when you look at number 2, you have the X. So here, when you have the X, you're going to standardize. But for question 1, we already have the values of Z. So let us go to the tables and read 2.7. We will also read 1.25. So let me share the tables. So I want from the class someone to tell me the value of 2.75 from the table. So you go down for the Z values where you have 2.7, it's here. And then 0.05 for the columns, It's here. This is the column for 0.05. So you go down up to where you have the Z value as 2.7.
In other words, they have to be 2 decimal places.
Yes.
You always have to have 2 decimals.
So this being the column for 0.05, we go down up to where we have 2.7. This is the value 0.9970. We had the value of 1.25 previously, so we simply subtract. So there is an exercise whereby you have been given the mean and the standard deviation, and you have been given the ranges of x. You are required to find the z values from the table. So that's the exercise that you have for your practice, unless someone has a question. I will send
Just to
these
confirm.
notes.
Yes,
Yes.
Samuel?
Yeah, you've said we always read, we round up to 2 decimal places.
Yes.
Okay.
Because we have 2.75, 2.78 to 1.28. You see, the first row is 0.0 something, and the first column is 2 point something, or is point something. So it's like adding. You're adding, if you're saying 1.25, you add 1.2 plus 0.05, which is up there. So if there are more, then it means you will have to look for the other decimal places. So you just round it off to 2 decimal places so that you have, if it was 2.738, so we'll just say 2.74 so that we can be able to look for 2.7 and 0.04.
Thank you.
Okay, let us try this. Let us try just this. Then there's something I want to point out. Suppose x is normal with mean 2. Now, Angela, there we have to be very clear. Are we talking about the variance or the standard deviation? Because sometimes some books give the n sigma, some give n sigma squared. But
This book
yours
it's
is
the
n.
standard deviation.
Yes, yours is n sigma. But it has to be very clear. In most cases, they give n sigma squared. So that 16 is sigma squared. So we would have sigmas 4. But assuming that is the sigma, and this one, mu is 3. Is it 2 or 3?
Mu is 3.
Mu is 3.
Yeah.
So let us get the first one. Probability that x lies between 4 and 8. Let's try it. Anybody who has gotten something, we want to interrogate it just to see whether we are getting. X between 4 and 8. Mu is 3, sigma is 16.
I got it as 0.1676, the final answer.
What did you do?
After standardization,
Mm-hmm.
I got the Z ranges from 0.06 to 0.5. So I read for 0.5.
So it is 4 minus 3 over 16.
Yes.
0.06. The other one is 8 minus 4 over 16.
It was minus. I did minus 3.
Sorry, 8 minus 3, not minus 4. 8 minus 3 over 16.
0.5.
Exactly.
So I read from the table for 0.5, it is 0.6915.
Then you subtract for
0.06, which is 0.5239.
So you get
0.1676.
I think that's right. Anybody who got something different? Moses Gray? Moses, are you there?
I got negative 0.0625. Then less than or equal to Z, less than or equal to 0.3125.
Oh, your Z is from negative to positive.
Yeah.
But we have 4 to 8, Amma? Is it not X is from 4 to 8?
Yeah, let me check that.
Yeah, so 4 minus 3. 4 you subtract 3, that cannot be negative. The numerator is 4 minus 3 over 16. 4 minus 3 is 1. It can't be negative. Yeah, unless you did it the other way around, 3 minus 4. Brian Kimondo, is it what we got earlier is fine? Brian Kimondo. Angela, now Kimondo is absent or he has left. You can see some people don't. Charles Esinyen Ekale? Charles Ekale?
Yes, sir.
Yes. What did you get? Is it the earlier one or what Moses got?
The earlier one.
The earlier one. So you're fine, eh?
Yes, I'm fine.
Emmanuel Otieno, are you okay?
Yes, I'm okay.
Fine. Yeah, so that is
excuse
a
me,
simple
sir.
one. You just subtract, because it is saying X, we can't read it from the table, so we have to standardize it. Standardizing mean you what? You subtract the mean and divide by the standard deviation. Don't divide by the variance. You divide by the standard deviation. That's why I say the Z score is X minus mu, that is the measurement X, minus the mean divided by the standard deviation. That gives you the Z score. What was the second one, Angela? X is between?
X is between 0 and 5.
Let's try that. X between 0 and 5. Let's try X between 0 and 5. Mu is still 3. Sigma is 16. There are no ladies in class today. I can't see any. 0 and 5.